Hello and welcome to this further maths video on finding the perpendicular distance from a point to a plane, and we'll look at some questions on reflecting points in planes. So in the formula book you are given an equation or a formula that will find the shortest distance from a point to a plane. So if you've got a piece of paper and you're trying to find the shortest distance, you can probably visualize it quite well. The thing you have to be careful with this formula is we often have equations of planes equal to a number. But for the formula in the formula book, they put it equal to 0, which is, of course, a number. But you need to watch this sign of the D. That is the thing where you will make a mistake. So we'll see how that works in a minute. But if you've got the equation of a plane in this form, then if you substitute that into this formula, and you can find the distance from a particular point. So let's have a look at how this works in practice with a particular question. So we've got a plane here, I plus 2j plus 2k dot r equals 5. And we've got a point, and we want to find the shortest distance between P and the plane. So we need to change this into an equation of the plane that looks like the form, particularly that you've got in your formula book. So if you substitute x, y, and z for your general point R, then you've got that x plus 2y plus 2z equals 5. But like I said before, this has got to be equal to 0 in this formula, so we need to write it as x plus 2y plus 2z minus 5 equals 0. The point is 1, 3, minus 2. So that's your alpha, beta, gamma up here. So the perpendicular distance is given by this formula. So this formula says m1, n2, n3. That's the normal here. So that's going to be, but instead of x, y, and z, we're going to substitute in the x, y, and z coordinates of our point. So we're going to have 1, I substitute 1 in there, plus 2 times 3, plus 2 times minus 2, minus 5, because this is our equation here. All of that is going to be over n squared, m1 squared, n2 squared, n3 squared. That's the modulus of the normal. So that's going to be 1 squared plus 2 squared plus 2 squared, square rooted. And when you work all of this out, you get the modulus of minus 2 over 3, which is 2/3. So that is the shortest distance from this point to this plane. Part B of this question asks you to reflect this point in the plane, and you're going to get the answer Q, and you want the coordinates of Q. So a diagram helps a lot here. Here is our plane, and here's our point P. And we want to reflect that. So it's going to go down to there, and then it's going to end up there. That's going to be where Q ends up. So this is the plane. I'm going to call that point there M, because that's the midpoint of that line in a reflection. So the overall method for doing this is to find an equation for PQ, find out where it intersects the plane. We've got a line and a plane, find where it intersects the plane, work out the value of lambda that takes you from P to M, and then double that because it's going to be double in the reflection. So the equation of PQ, so the equation of PQ, well, the equation of a line is a point on the line, which we know P is 1, 3, minus 2, plus lambda times the direction vector. Now, the direction vector of this is the normal of the plane because we are moving perpendicular to the plane. So that's 1, 2, 2. We know that m is on the plane and m is on the line. So if m is on the line, O to m is equal to a general point on the line, which is 1 plus lambda, 3 plus 2 lambda, minus 2 plus 2 lambda. And we know that m is also on the plane. So m is on the plane. So if I put this point here into my vector equation of the plane, it should be equal to 5. So I've got 1 plus lambda, 3 plus 2 lambda, minus 2 plus 2 lambda, dot 1, 2, 2 equals 5. And this gives me, when I work out this equation, 1 plus lambda plus 6 plus 4 lambda minus 4 plus 4 lambda equals 5. And when you tidy this up, you get lambda is 2 over 9. So that value of lambda takes me from P to M. But what I need to get from O to Q. So how do I get from O to Q? Well, O to Q is going to be starting off here, O to P, but I'm going to travel 2 lots of that value of lambda, because the first value of lambda being 2/9 gets me to there. But I want to go twice that distance, so I want to do 2 lots of that. So this is another lambda is 2 over 9. So I need to do 2 lots of 2 over 9 multiplied by 1, 2, 2. And when you work that out, you get 13 over 9, 35 over 9, and minus 10 over 9. These questions don't always work out nicely, so you have to be prepared for that. So that's the general method for finding a point of reflection. Right, the second question, or the last question, which is a stretch and challenge question here, asks you to find the equation of a line when it's been reflected in a plane. Now, this is quite a difficult question. That's why it's got a stretch and challenge logo at the top. And what's going on with this question is you've got a plane like this, you've got a line, and we're going to reflect the line. So the line actually intersects the plane like this. So there's my line, L1, and we're going to reflect it down like that. So those should be dotted really. Here's L2 coming down like that. So that's the reflection of that line. And the question wants you to find a vector equation of this line here. So the general method for this is to find the intersection of the first line in the plane, then find a point here and find where that ends up, and then work out the equation of this line. So the solution to this is in the textbook, and here is a work solution just to save a lot of writing. This is a difficult question, and you will take a couple of times to really get to grips with this. So the first step is to convert this line here into a vector form. So 2, 4, minus 6 is your point on the line, so that's your P, and you've got the direction vector of this line here is going to be 2, minus 2, 1, because that's the bottom numbers of that. We've got the plane, 2 minus 3, 2x minus 3y plus z equals 8. So there's the equation of the plane in vector form. First of all, find the intersection of the line and the plane. So I'm going to put my general point for the line, do the dot product with the normal for the plane, and it's going to be equal to 8. And that gives me lambda is 2. So I can now work out the coordinates of the point where the line meets the plane. So that's O to A. So I can work out, I know what O to P is. I know this point here is 2, 4, minus 6. So I want to find this reflected point here, because if I can find the coordinates of this point here, and I know that point there, I can work out the equation of that line. So we do what we did before. We reflect this point P down to here. So we work out the intersection of the line through P, normal to the plane. So that's this line coming down here. And that gives us this point M. So this is like the last example. We'll work that out, and we get that mu is equal to minus 11 over 7. It's not a very nice answer at that point, but that is how this question works out. So we now know how to work out O to P dash. So O to P dash is O to P plus 2 times 11 over 7. And that gives me the coordinates of O to P as being this here. This is not, the numbers work out really uncomfortably here. So now I want the equation of this line, this line here, A to P dash. So that's going to be 6 naught minus 4. That is the point where it intersects. So that's A, plus T times the vector from A to P. So now you've got to work out the vector from A to P, which again isn't very nice. And you end up with this here. Because these are all over 7 when you work out A to P, you can take the 7 out and write it as, and divide by 2 to get this answer here. So try to understand the overall outline of how this question is solved without thinking too much at this stage about the detail. If you want to reflect a line, then what you're going to do is find where does that line intersect the plane? Where does the point P reflect to? And then what is the equation that takes you from A to P dash?